here it is, the oldest companion humanity has ever known. It has watched every night of every human life that has ever been lived on this planet. Every campfire, every civilization, every dream whispered into the darkness. The moon has been there, watching from its perch above the world, unchanged, unhurried, eternal. And yet, we barely know it. Not really. We think we do, because we can look up and see it, because it's familiar, because it rises and sets and sometimes turns the color of a dying ember and sometimes disappears entirely. We mark our calendars by it. We write poetry about it. We name our children after it. We've walked on it. But there are things the moon keeps hidden, secrets pressed into its ancient dust, mysteries that science is only beginning to unravel, and some that still have no answer at all. Welcome to Infinite Science. Tonight we travel to the moon, not the moon of textbooks and diagrams, but the moon of strange truths, of startling science, of deep wonder. A world that looks simple and familiar, and yet, when you press your understanding against it, dissolves into something far more complex, far more strange, far more beautiful. The moon you thought you knew is only a mask. What lies behind it is far more interesting. Let's begin. 4.5 billion years ago, the Earth was not a place you would recognize. It was younger, slightly smaller, still in the process of becoming. The solar system itself was an unruly neighborhood, full of debris, full of wandering rocks and nascent planets jostling for position around the young sun. The sky, if you could call it that, was not blue. It was the color of disaster. And then something happened that would change the Earth forever. Something enormous came. We call it Theia. It was not a small rock. It was a world, a protoplanet approximately the size of Mars, which means it was roughly half the diameter of Earth. It had its own gravitational history, its own composition, its own kind of silence. And it was on a collision course with everything we would ever become. The impact, which scientists call the giant impact hypothesis, and which is currently the most widely accepted explanation for how the moon was born, was not a gentle thing. It was not a glancing brush, not a near miss. It was full, catastrophic contact. A collision so enormous that the mind genuinely struggles to hold it. The simulation software we use today gives us something that ancient humans could never have conceived of: a way to watch it happen. And what you see when you watch the collision unfold in computer models is almost artistic in its violence. Two worlds becoming one, and in that becoming, casting off a ring of debris so hot and vast that it wraps the new, larger Earth in a shroud of vaporized rock. That debris, that spray of molten silicate, that cloud of Earth stuff and Theia stuff, already beginning to mix and cool and orbit, is where the moon was born. Within, perhaps a few thousand years, a geological eye blink, the debris began to coalesce. Gravity pulled it together. The lighter elements, the ones that had risen to the surface of both planets before the impact, were disproportionately represented in that debris ring. This is why the moon has almost no iron core. The iron, being heavy, stayed in the Earth. What flew outward was mostly rock, and rock became the moon. But here is where the story becomes strange. And it becomes strange in a way that has nagged at planetary scientists for decades. If Theia and Earth collided and mixed, as the models suggest, then the moon should carry a chemical signature, a record of being partly Theia and partly Earth. Its rocks should differ subtly but measurably from Earth's rocks. They don't. The moon's rocks, brought back by Apollo astronauts in the late 1960s and early 1970s, are chemically almost identical to Earth's. Not similar, almost identical. The ratio of oxygen isotopes, for instance, which varies distinctly from one body in the solar system to another, is essentially the same in lunar rocks as it is in Earth's mantle. This should not be the case if Theia was a separate world with a separate origin. Various explanations have been proposed. Perhaps Theia formed in the same part of the solar system as Earth, making it compositionally identical. Perhaps the collision was so energetic that the material mixed so thoroughly that Theia's identity was completely absorbed. Perhaps there were multiple smaller impacts rather than one giant one. Perhaps the current hypothesis, despite its elegance, is missing something fundamental. We do not know. This is not a failure of science. It is science working exactly as it should, sitting with ambiguity, holding the question open, refusing to collapse into a false certainty. The moon's birth remains one of the great open puzzles of planetary science. We have the broad shape of the answer. The details keep shifting. And this, perhaps, is the most honest thing we can say about the moon. It has been here since nearly the beginning, and it still surprises us. But the moon's strange story did not end with its formation, because almost immediately, in cosmic terms, the two worlds began to drift apart. And they are still drifting. There is something happening right now as you watch this that you cannot see or feel. Something quiet and continuous and, in a geological sense, quite dramatic. The moon is moving away from us. Not dramatically, not at any speed you could observe over a human lifetime, but consistently, measurably, verifiably. The moon recedes from Earth at a rate of approximately 3.8 centimeters per year. That's roughly the rate at which your fingernails grow. It doesn't sound like much. Over the course of a single human life, the moon will have retreated a little less than 3 meters from where it started. Over a century, less than 4 meters. You could walk that distance in a few seconds. But time is patient in ways that humans are not. When the moon formed, it was not 384,000 kilometers away. It was closer, much closer, possibly as near as 20,000 to 30,000 kilometers from Earth's surface. Imagine the moon taking up an enormous fraction of the sky, its disk perhaps 10 to 20 times larger than what we see today. Imagine the tides it would have driven. Colossal walls of water, sloshing back and forth across the young Earth's ocean with an intensity that dwarfs anything in modern experience. The early Earth would have had tidal ranges not of a few meters, but of hundreds of meters, perhaps more. That proximity was the engine of the recession, and the mechanism, tidal friction, is one of the most elegant and underappreciated processes in all of planetary science. Here is how it works. The moon's gravity pulls on the Earth. This is familiar to most of us as the mechanism behind the tides. The ocean bulges slightly toward the moon, and slightly away from it on the opposite side. And as the Earth rotates, those bulges sweep around the planet, creating the rhythmic rise and fall we call tidal cycles. But here is what is less intuitive. The Earth itself is not rigid. The solid rock of the crust and mantle flexes very slightly under the moon's gravitational pull. And because the Earth is rotating faster than the moon orbits, a day is shorter than a lunar month, the tidal bulge is dragged slightly ahead of the moon's position. The Earth is, in a sense, carrying the bulge forward with it. This ahead-of-center bulge exerts a gravitational pull on the moon. And because the bulge is slightly ahead, not directly beneath the moon, but slightly in front of it in the direction of orbit. This pull is not pulling the moon straight toward Earth. It's pulling it very slightly forward, in the direction of the moon's own motion. And what happens when you continuously accelerate something that is orbiting a planet? It spirals outward. This is one of those cases where physics does something beautifully counterintuitive. You might expect that pulling the moon forward would just speed it up. But in orbital mechanics, speeding up an orbiting body causes it to move into a higher, larger orbit. And in a larger orbit, it actually moves more slowly. The moon gains energy, but uses that energy to climb further from Earth rather than to accelerate. It's as if you gave a stone in a sling extra force, and instead of swinging faster, the sling simply grew longer. As the moon moves outward, there is a reciprocal effect. The Earth slows down. Conservation of angular momentum demands it. The same tidal friction that propels the moon outward is also breaking the Earth's rotation. Days on Earth are getting longer, by about 1.4 milliseconds every century. In the deep past, when the moon was closer, this effect was far more pronounced. Geological records, including certain microscopic patterns in ancient corals and tidal sediment layers called tidalites, suggest that 1 billion years ago, a day on Earth lasted only about 18 to 19 hours. The moon has been gradually gifting Earth with longer days, and Earth, in exchange, has been gifting the moon with distance. This process, left to continue indefinitely, would eventually lead to a system in which the Earth's rotation period equals the moon's orbital period, meaning Earth would eventually show the same face to the moon at all times, just as the moon currently shows the same face to Earth. But calculations suggest that this would take far longer than the remaining lifetime of the Sun, so it will never actually occur. Instead, long before that equilibrium could be reached, the Sun will swell into a red giant and the entire system will be consumed or dramatically altered. So, the moon recedes, the days lengthen, and everything eventually ends. Not with drama, but with the patient arithmetic of physics. Somehow, that feels appropriate for the moon. We have been measuring the moon's recession with extraordinary precision since the Apollo program left behind a peculiar gift: small arrays of mirrors on the lunar surface called retroreflectors. These mirrors are designed to bounce laser beams fired from Earth directly back to their origin, regardless of the angle of incidence. By timing how long it takes for the laser pulse to travel to the moon and return, we can calculate the distance to within a few centimeters. Scientists have been doing this since 1969. The measurement has been repeated thousands of times by observatories on multiple continents, and every measurement confirms the same gentle, inexorable truth. The moon is leaving. 3.8 centimeters per year. It's almost tender, isn't it? Across the entire span of human history, from the first cave paintings to the Renaissance to the Industrial Revolution, no human being had ever seen the far side of the moon. Not once, not through any telescope, not from any ship or mountain or high place on Earth. It was simply invisible. And then, on October 7th, 1959, a Soviet spacecraft called Lunar 3 swung around the far side and sent back the first grainy photographs. Humanity saw the moon's hidden face for the first time. And it was strange. It was very different from the side we knew. But why is one side hidden at all? The answer is a process called tidal locking, and it is both simple and deeply fascinating. Cast your mind back to the early moon, newly formed, still hot and plastic from the violence of its birth. In those early days, the moon rotated on its own axis just as any other body would. Spinning freely, its day and night cycling independently of its orbit around Earth. But the moon was close to Earth. Very close. And Earth's gravity, enormous, insistent, acted on the moon the same way the moon acts on Earth. It created tidal forces. The near side of the moon was pulled more strongly than the far side. This created a slight elongation in the moon's shape, a tidal bulge, pointing roughly toward Earth. Now, if the moon's rotation was not synchronized with its orbit, if the moon was rotating faster or slower than its orbital period, This elongation would be dragged around, and Earth's gravity would exert a torque on it, a twisting force. Think of a bar magnet being pulled toward a magnetic field. If it's not aligned, the field will try to align it. Earth's gravity was the field. The moon's elongation was the magnet. Over millions of years, that gravitational torque gradually slowed the moon's rotation until the moon's rotation period exactly matched its orbital period. At that point, the elongation always pointed toward Earth. Earth's gravity had nothing to grab onto anymore, no misaligned bulge to push or pull. The moon had found its equilibrium, and in finding that equilibrium, it locked one face toward Earth forever. This is called synchronous rotation, or tidal locking, and it is not unique to the moon. It is an extremely common outcome in the solar system wherever a smaller body orbits close to a much larger one. Most of the large moons of Jupiter and Saturn are tidally locked to their parent planets. Pluto and its moon Charon are mutually tidally locked. They show the same faces to each other, two bodies in an eternal face-to-face embrace. But the Earth-Moon system is the most famous example, and perhaps the most personally felt, because the consequence that played out across all of human history, is that we lived for hundreds of thousands of years wondering what lay on the other side. The far side, when finally revealed, is a world of startling contrasts with the near side. The near side, the face we know, has vast dark plains called Maria, Latin for seas, named by early astronomers who mistook them for bodies of water. These Maria are ancient lava flows, the solidified remnants of vast volcanic eruptions that filled the moon's great impact, basins billions of years ago. They cover about 31% of the near side. The far side? The far side has almost no Maria at all. Only about 1% of the far side is covered by these dark volcanic plains. Instead, it is a relentless, churned landscape of craters. Impact craters upon impact craters, a record of ancient bombardment so dense that new craters have largely just overwritten old ones, creating a terrain called the heavily cratered highlands that geologists sometimes describe as saturated with impacts. Why the difference? This is one of the genuine unsolved mysteries of lunar science. One compelling hypothesis involves the moon's interior during the time when the Maria were being formed, roughly 3 to 4 billion years ago. The near-side crust is, on average, thinner than the far-side crust. Thinner crust means magma from the interior could more easily erupt through it. The far side's thicker crust acted as a barrier, preventing volcanic activity from reaching the surface even when large impact basins were present and magma was plentiful. But why is the near side crust thinner than the far side? This is where the mystery deepens. Some researchers suggest that in the early moon, before the crust solidified completely, the still molten interior was being kept warmer on the near side. Heated by the proximity of Earth's thermal radiation and gravitational influence. This would have caused the solidifying crust to be thicker on the cool far side. Others have proposed that a second, smaller moon may once have existed and eventually collided gently with our moon, depositing a thick layer of additional material on one hemisphere, creating the crustal asymmetry we see today. This binary moon hypothesis has attracted significant attention since it was proposed in 2011. The data from NASA's Grail mission, which mapped the moon's gravitational field with extraordinary precision in 2012, has given us detailed information about the moon's interior structure, but has not fully resolved the question. The far side remains in some respects as mysterious as it was before Lunar 3 photographed it. There is something philosophically resonant about the far side. All of human history occurred under the gaze of the moon's near side. Every civilization, every era, every great event was witnessed by those familiar craters and plains. The far side has never seen humanity. It faces outward toward the galaxy, seeing nothing of us. In 2019, China's Chang'e 4 spacecraft became the first mission to land on the far side of the Moon. A technical achievement made extraordinarily difficult by the fact that the far side, by definition, cannot communicate directly with Earth. Mission controllers had to use a relay satellite positioned at the L2 Lagrange point behind the Moon to maintain contact. The lander and its small rover, Yutu-2, touched down in the von Karman crater within the enormous South Pole Aitken Basin, one of the largest and deepest impact craters in the entire solar system. The mission continues to this day, quietly exploring the side of the Moon that humans never knew. The Moon appears from a distance to be utterly dead. No wind, no weather, no erosion in the conventional sense, no rivers or glaciers carving the landscape, just rock and dust and time. And yet, the Moon is not entirely still. It shakes, not often, not dramatically, but with a consistency and a character that surprised scientists enormously when the Apollo missions left behind seismometers, sensitive instruments designed to detect vibrations in the lunar ground, and began receiving data. Between 1969 and 1977, the Apollo seismic network detected thousands of moonquakes, and what the data revealed was not what scientists expected. Because when you compare a moonquake to an earthquake, you notice something striking. Earthquakes are relatively sharp. They rumble, they peak, they fade. The seismograph needle swings violently and then settles back toward, quiet within a matter of minutes. This is because the Earth's interior is warm, wet, and fractured in ways that absorb and scatter seismic energy efficiently. The rock is saturated with fluids, full of microfractures, malleable in ways that dampen vibration. A moonquake is different. When a moonquake hits the lunar surface, the Moon doesn't just shake and settle. It rings. The famous description from the mission controllers and scientists at the time was that the Moon behaved like a bell when struck. It rang and rang and rang, the vibrations continuing far beyond what anyone expected. One particularly dramatic moonquake, triggered by the intentional impact of the Apollo 12 ascent stage with the lunar surface, produced seismic waves that continued for more than 55 minutes. This extraordinary resonance occurs because the Moon's interior is cold, dry, and extraordinarily rigid. There is no fluid to absorb the vibrations, no warm plastic rock to damp them out. Seismic energy propagates through the lunar interior and bounces back and forth, interfering with itself, sustaining itself far longer than any comparable event on Earth. Moonquakes come in several varieties, and each is fascinating in its own right. The deepest moonquakes occur at depths of around 700 to 1,200 kilometers, nearly halfway to the Moon's center. These are triggered, remarkably, by tidal forces. As the Moon moves through its slightly elliptical orbit, changing its distance from Earth throughout the month, the tidal stresses on the Moon's interior fluctuate. This periodic squeezing and releasing generates quakes at regular, predictable intervals tied to the lunar month. Scientists have catalogued hundreds of these deep moonquake clusters, and many return reliably, as if the Moon is ticking. Shallow moonquakes are a different and more dramatic category. They occur at depths of 50 to 200 kilometers, and they are far stronger. Some measured at around magnitude 5 on the Richter scale, which would be sufficient to topple furniture or knock objects off shelves on Earth. These shallower quakes are not periodic and not tidally predictable. Their cause is less well understood. Some researchers believe they may be related to the gradual cooling and contraction of the moon's interior over time. The slow thermal shrinkage of a world that has been losing heat for billions of years, its crust cracking and adjusting as the interior contracts. There are also thermal quakes, triggered by the extreme temperature swings of the lunar day. When the sun rises over a region of the lunar surface, temperatures can jump from around -180 degrees Celsius in the pre-dawn darkness to well above 100 degrees Celsius in direct sunlight in the span of a few hours. This violent thermal cycling, heating and then cooling, expanding and then contracting, causes the upper few meters of the lunar surface to crack and groan with a population of small, shallow quakes concentrated around local sunrise and sunset. And finally, there are the impact-related events, meteoroids and micrometeoroids striking the surface, each impact sending ripples through the moon's rigid body that the seismometers can detect. The moon, lacking an atmosphere, has no protection from these impacts. Rocks and dust particles that would burn up harmlessly in Earth's atmosphere reach the lunar surface at full cosmic velocity, and even small impacts leave a seismic signature. Now, the seismometers left by Apollo have long since ceased functioning. But the story is not over. NASA's Lunar Geophysical Network, planned as part of the Artemis program's infrastructure, envisions new seismometers on the lunar surface, more sensitive, more strategically placed, capable of giving us a truly three-dimensional picture of the moon's interior structure. With enough seismometers in enough locations, scientists could use the travel times of seismic waves to map the moon's interior the way a doctor uses ultrasound, to map the inside of a body. We would finally know whether the moon has a solid inner core, a liquid outer core, and exactly how the mantle is structured. We suspect it does, but we don't know for certain. A world we have visited and still don't fully understand. Have you ever noticed it? The moon just above the horizon, hanging low, appearing enormous, 3-4 times the size it seems when it's high overhead. The kind of moon that stops you mid-sentence. The kind of moon that makes people reach for their phones. And then, hours later, you look up, and the moon has climbed to the top of the sky, and it looks small, distant, ordinary. You haven't moved. The moon hasn't changed. Its distance from you is essentially the same. But something about the way it looks is completely different. What is happening? This is the moon illusion, and it is one of the most studied and argued about phenomena in the psychology of visual perception. It has fascinated philosophers, scientists, and curious observers for at least 2,000 years. Aristotle wrote about it. Al-Haytham, the medieval Arab scientist who founded modern optics, wrote about it. Modern psychologists still argue about the precise mechanism behind it. First, let us be absolutely clear about what is not happening. The moon on the horizon is not actually larger. Its angular size, the fraction of your visual field it occupies, is, if anything, very slightly smaller when it's on the horizon than when it's high overhead, because when the moon is on the horizon, you are slightly farther from it, by about 1 Earth radius, since you're looking across the surface of the planet rather than through it. If you were to photograph the horizon moon and the overhead moon and measure them carefully, the horizon moon would be fractionally smaller. It is entirely an illusion, a product of your brain, not the physical world. But the question of what produces the illusion has proven surprisingly difficult to resolve. The oldest explanation, which dates back to ancient times and was formally elaborated by mathematicians in the medieval Islamic world, is called the apparent distance theory. According to this view, when we see the moon on the horizon, our visual system, our brain's machinery for interpreting what our eyes tell us, registers the horizon as being very far away. We know from a lifetime of visual experience that objects on the horizon are distant. The brain, seeing a large-looking moon on a distant horizon, resolves the contradiction by making the moon appear physically large. The moon must be big, the brain reasons, because it's far away and yet subtending this angle. When the moon is overhead, however, there are no distance cues. The empty sky gives the brain nothing to anchor its distance estimate to. Without a sense that the moon is far away, the brain simply sees what the eye delivers, a disk of a certain angular size. Nothing is making it seem big. This explanation has intuitive appeal. But it's not universally accepted because some people see the illusion even in planetarium settings where there is no actual horizon, and the size of the illusion varies considerably between individuals in ways that pure distance estimation theory doesn't fully predict. A competing theory focuses on the apparent angular elevation of the moon. When the moon is on the horizon, our eyes are essentially level, looking straight ahead. This is the posture we adopt when looking at objects at eye level, which in our evolutionary and daily experience tend to be close. Objects at eye level seem close. The visual system may code a horizon moon as closer and compensate by inflating its apparent size. When we look at an overhead moon, we tilt our heads back. We're looking upward. In our experience, the things we look up at tend to be far away. Clouds, the sky, distant mountains. The overhead moon is placed perceptually in the category of far things. A third theory, proposed by researchers including Hershenson and later elaborated by Enright, involves the way our eyes change focus and convergence in response to the moon's position. Looking at a horizon moon, the eyes are in a state more consistent with near viewing. This physiological state may trigger size expansion. Probably the truth involves several of these mechanisms interacting. The visual system is not a camera. It is a storytelling machine, constructing a version of reality from incomplete information, using assumptions built up over a lifetime of moving through a physical world. The moon illusion is a beautiful case where those assumptions, usually so helpful, lead us momentarily astray. The moon hasn't changed. Your brain has. And in its small deception, the brain is doing something rather profound, reminding us that what we see is not reality. It is a model of reality. A very good one, but not the same thing. The moon, as always, is more than it appears. Every now and then the moon does something remarkable. It disappears the sun. Not dimly, not partially, completely. It covers the sun's disk with such precision that only the corona, the sun's outer atmosphere, remains visible. A halo of plasma streaming millions of kilometers into space, ordinarily invisible against the sun's blinding brightness, but in the brief minutes of totality, suddenly and breathtakingly revealed. A total solar eclipse, one of the most profound natural experiences available to a human being. People who have seen one describe it, almost universally, as transcendent, as one of the most beautiful things they have ever witnessed. Many devote years of travel and planning to chasing them across the globe. And the reason they are possible, the reason they happen at all, is an almost unbelievably precise coincidence. The sun is approximately 400 times larger than the moon. The sun is also, at this particular moment in Earth's history, approximately 400 times farther away from Earth than the moon. The result? From the surface of Earth, the sun and the moon have almost exactly the same apparent angular diameter. They are, visually, the same size. The moon can cover the sun almost perfectly, not leaving a huge gap on one side, not leaving a huge gap on the other. With extraordinary, almost sculptural precision, it fits. No other planet in the solar system enjoys this coincidence. Mars has two moons, Phobos and Deimos, but both are far too small to cover the Sun from Mars's surface. They produce only small, dimming transits, not total eclipses. Jupiter and Saturn have large moons, but those moons and those planets are so far from the Sun that the geometry doesn't work in the same way. Earth is the only planet in the solar system where a moon produces total solar eclipses, where a natural satellite covers the Sun's disk exactly. And this coincidence is temporary. Remember that the moon is receding from Earth at 3.8 centimeters per year. As it moves farther away, its apparent angular size in Earth's sky becomes smaller. We are currently living at the precise point in Earth's history. And the window is perhaps 600 million years wide, which sounds enormous but is a small fraction of Earth's 4.5 billion year lifespan. When the moon's distance and the sun's distance are in the right ratio for total eclipses. In the distant past, when the moon was much closer, it would have covered the sun with substantial overlap. The corona would have been hidden behind the moon's extended shadow. In the distant future, the moon will be too small to fully cover the sun, and total solar eclipses will be replaced by annular eclipses. A ring of sunlight still visible around the moon's diminished disk. For the brief cosmic window in which we find ourselves, the geometry is perfect. Why does this matter, beyond its visual spectacle? Because total solar eclipses have been scientifically transformative. The first confirmation of Einstein's general theory of relativity came from observations made during a total solar eclipse. In 1919, astronomers Arthur Eddington and Frank Watson Dyson led expeditions to observe the eclipse of May 29th of that year. Einstein's theory predicted that massive objects bend the path of light, passing near them, a phenomenon called gravitational lensing. During totality, stars near the edge of the obscured sun should appear slightly displaced from their expected positions because the sun's gravity would be bending their light. The observations confirmed Einstein's prediction. General relativity was validated, and science and our understanding of the universe was changed forever. All because the moon was the right size, at the right distance, at the right time. The helium we know exists in the sun was discovered during a total solar eclipse. The strange structure of the solar corona, with its million-degree temperatures that dwarf the visible surface temperature beneath. It, one of solar physics' great mysteries, was extensively mapped during eclipses before space-based coronagraphs made it possible to study the corona at any time. Eclipses have shaped science, and the coincidence that makes them possible is one that seems, in its precision, almost impossible to account for by chance alone. It is not impossible, of course. It is simply what happens to be true in our particular solar system at this particular point in time. The physics doesn't require it. And yet, here we are, standing under a perfectly darkened sky, watching the sun disappear. There is a reason Earth has been habitable for billions of years. Multiple reasons, certainly. The right distance from the sun, the right atmosphere, the right chemistry. But one reason is less commonly appreciated, and it has a name: the moon. Earth rotates on an axis, a tilt of approximately 23.5 degrees from vertical, relative to the plane of its orbit around the sun. This tilt is the reason for seasons. When the northern hemisphere is tilted toward the sun, it is summer in the north and winter in the south, and vice versa. Without axial tilt, Earth would have no seasons. The same regions would always receive the same amount of sunlight. But here is the crucial thing: that tilt needs to be stable over long timescales for the climate to be stable. A planet whose axial tilt wanders dramatically over millions of years would experience catastrophic climate swings, periods of extreme heat when the poles faced the sun for prolonged periods, periods of severe cold when they didn't. Life trying to establish itself on such a world would face a relentlessly hostile environment. This is almost exactly what happens on Mars. Mars has no large moon. Phobos and Deimos are tiny captured asteroids, essentially irrelevant for stabilizing Mars's orientation. Without a significant moon, Mars's axial tilt has been free to wander under the gravitational influence of the other planets, particularly Jupiter. Computer simulations show that Mars's tilt has varied from near zero to perhaps 60 degrees over geological time, with profound effects on Martian climate, potentially explaining why Mars has polar ice caps of varying size and may have had episodic periods of liquid water that would then freeze again as the tilt changed. Earth's tilt, by contrast, has remained within a range of roughly 22 to 24.5 degrees over the past 41,000 years, varying in a gentle cycle. This stability is not accidental. The Moon, massive and close, acts as a gravitational anchor on Earth's axis. The Moon's gravitational influence suppresses the resonances between Earth's axial wobble and the orbital frequencies of the other planets. Resonances that would otherwise allow those planets, especially Jupiter, to gradually destabilize Earth's tilt. The Moon, in effect, shields Earth from Jupiter. The implications of this stabilization are profound. A planet whose axial tilt stayed roughly constant for billions of years would maintain relatively consistent climate zones. A stable tropics, stable temperate regions, stable polar conditions. Life evolving in such an environment would not be repeatedly wiped out by catastrophic climate shifts driven by orbital geometry. Complex life, multicellular life, life with seasons adapted into its biology, could develop and persist. A planet with chaotic axial tilt might still develop life, but the challenges would be immense. Every few tens of millions of years, the climate could shift so dramatically that mass extinctions would be a near certainty. How different would Earth's history be without the Moon? It's one of the most fascinating counterfactuals in astrobiology. Some researchers have proposed that life on Earth might still have originated. Life, once it gets started, shows extraordinary resilience. But that complex, differentiated, multicellular life might have taken far longer to emerge, or might not have emerged at all. The Cambrian explosion, the great diversification of animal life that occurred roughly 540 million years ago, required not just the right chemistry and the right temperature, but hundreds of millions of years of relative climatic stability in which increasingly complex organisms could evolve without being periodically reset. The Moon may have given us that stability. Of course, this is not a settled conclusion. Some researchers argue that the chaotic variation in Earth's tilt would not have been as severe as on Mars even without the Moon, because Earth's much larger size and greater rotational angular momentum would have provided some inherent stability. The debate continues, but the weight of current evidence and simulations suggests that the Moon is not a passive spectator in Earth's habitability story. It is an active participant, a gravitational, steadying hand that may have been one of the preconditions for the world we know. The Moon does not just light our nights. It may be the reason we are here at all. The Moon looks from a distance uniformly grey, soft, almost powdery. The footage from the Apollo missions shows astronauts leaving perfectly preserved footprints in a surface that looks like fine sand. The kind of thing you'd want to run your fingers through. Don't. Lunar dust, the fine regolith that covers the Moon's surface to depths of several meters in most places, is one of the most underappreciated hazards of space exploration. And understanding why requires understanding the very different process by which lunar dust is made. On Earth, dust and sand are shaped by process. Water, wind, and geological activity grind and tumble rock particles against each other, smoothing their edges, eroding their sharpness. Beach sand is beautiful, precisely because it has been worn smooth over thousands of years of abrasion. Even desert dust, which can cause significant lung damage, is relatively rounded compared to fresh rock particles. Lunar regolith has not been shaped by any of these processes. The moon has no weather, no liquid water, no wind. Its dust is produced primarily by micrometeorite impacts, a constant, slow rain of tiny particles striking the surface over billions of years, shattering rock into smaller and smaller fragments. These fragments are never tumbled. They are never polished. They remain sharp. Sharp in a way that is difficult to convey without resorting to the word that most accurately describes them. They are like microscopic glass shards. The Apollo astronauts discovered this the hard way. After moonwalks, they would return to the lunar module and find that their equipment was covered in dust, and not just lightly coated, but impregnated. The dust clung to everything, to spacesuits, to equipment, to gloves. It worked its way into joints and hinges. It abraded optical surfaces. The fine particles were electrostatically charged. On the moon's sunlit surface, the solar wind and ultraviolet radiation knock electrons from dust particles, giving them a positive charge that makes them cling to surfaces and to each other. Apollo 17 astronaut Harrison Schmitt suffered what he and the crew described as lunar hay fever. His nasal passages became irritated by dust that had been tracked into the lunar module and become airborne in the low-gravity environment. His symptoms lasted for the rest of the mission. The long-term health implications of lunar dust exposure are deeply concerning to mission planners. On Earth, we have extensive research on inhaled mineral dusts, silica dust, asbestos, coal dust, and the results are not encouraging. Fine, sharp particles that reach the deep lung, the alveoli, where gas exchange occurs, are extremely difficult for the body to clear. Macrophages, the immune cells responsible for removing foreign particles from lung tissue, can engulf them. But if the particles are too numerous, or if they are sharp enough to damage the macrophages themselves, they are not cleared efficiently. They remain in the lung, causing persistent inflammation and, over time, fibrosis, scarring. Lunar regolith is rich in silica, which is a known lung hazard. Its particles are extraordinarily fine. A significant fraction fall in the respirable range, meaning they can reach deep into the lung. And they are jagged in a way that Earth silica dusts, which have at least some weathering, typically are not. Studies of lunar samples in the lab have shown that fresh lunar regolith, unweathered as it exists on the surface, is highly reactive chemically. Its surface chemistry is active in ways that might be particularly damaging to biological tissue. When scientists expose cells in vitro to lunar simulant, engineered materials designed to mimic lunar regolith's physical and chemical properties, they observe cell damage and signs of oxidative stress. Extended lunar missions, particularly those lasting weeks or months, could expose astronauts to significant quantities of regolith. Building habitats, excavating for resources, or simply moving around the surface continuously disturbs the dust. Without atmosphere, the moon offers no mechanism to settle or dilute airborne particles. Once agitated in an enclosed habitat, dust remains suspended far longer than it would on Earth. NASA and other space agencies are actively researching dust mitigation strategies. Electrostatic precipitators to pull charged dust from the air, special materials for suits that resist dust adhesion, airlocks with dust cleaning systems, surface conditioning to stabilize the regolith around habitats. It is one of the most pressing engineering challenges of human lunar exploration. The moon's surface is ancient, patient, and beautiful. It is also, in its quiet way, quite hostile. Somewhere on the surface of the moon, right now, there are boot prints, not just any boot prints. The boot prints of 12 human beings, the only 12 people in all of history who have ever walked on another world. Neil Armstrong, Buzz Aldrin, Pete Conrad, Alan Bean, Alan Shepard, Edgar Mitchell, David Scott, James Irwin, John Young, Charles Duke, Eugene Cernan, Harrison Schmitt. Those footprints were made between July 1969 and December 1972. And unless something disturbs them, an impact, a landslide, a future mission, they will remain there, perfectly preserved, for hundreds of millions of years, possibly longer. On Earth, a boot print in mud lasts until the next rain. A footprint in snow disappears at the next thaw. Tracks in sand are erased by wind in hours or days. The processes of our world are relentlessly corrective. Wind, water, temperature change, biological activity constantly reshape and erase the traces we leave. The moon has none of these processes. There is no wind to blow dust across the tracks, no rain to fill them in, no freezing and thawing to heave and distort the surface, no bacteria or plants or fungal networks slowly decomposing the disturbed material. The upper regolith is extraordinarily stable over human timescales. What is pressed into it stays pressed into it. The timescale over which the boot prints will survive depends on one erosive process that does exist on the moon: micrometeorite bombardment. Small particles, grains of cosmic dust moving at high velocity, constantly rain onto the lunar surface, and over very long periods of time this slow bombardment gradually churns and disturbs the upper layer of regolith. The process is called impact gardening. At the depths of a boot print, a few centimeters, the gardening rate is estimated to disturb and overturn the material on timescales of perhaps tens of millions to hundreds of millions of years. A boot print might remain recognizable for 1 million years, perhaps 10 million, perhaps longer in regions where micrometeorite flux is lower. The exact duration is uncertain, but the general answer is extraordinary. These 12 people left marks on another world that will outlast the entirety of human civilization. Every human language that has ever been spoken, every book that has ever been written, every building that has ever been built. The footprints will outlast us. The flags planted at the Apollo sites have a more complicated fate. The nylon fabric of the flags, exposed to the extreme UV radiation of direct solar illumination with no atmospheric protection, has almost certainly been bleached to white or degraded entirely by now. Ultraviolet radiation breaks the chemical bonds in fabric. Orbital photographs of the Apollo sites taken by NASA's Lunar Reconnaissance Orbiter have shown that the flags at 5 of the 6 sites are still standing. They cast shadows visible from orbit. But the Apollo 11 flag, which fell over when the ascent stage rocket exhaust hit it during liftoff, lies flat. White or faded flags, lying or standing. The equipment left behind is extraordinary in its variety and its historic weight. 6 lunar module descent stages, essentially the lower halves of the spacecraft the astronauts landed in. 3 lunar roving vehicles, the electric cars driven by the crews of Apollo 15, 16, and 17. Seismometers, laser retroreflectors, experimental packages, cameras, even some bags of human waste left behind to save weight for the return journey. All of it preserved, all of it quietly waiting. There is something deeply moving about this. The idea that the physical evidence of humanity's greatest adventure lies on another world, intact and untouched, slowly circling the Earth we came from. The dust has settled back over much of it. The shadows shift as the sun crosses the lunar sky. Occasionally, a micrometeorite strikes nearby, sending a tiny plume of dust drifting slowly back to the surface. And it all sits there, patient, waiting for whoever comes next. Close your eyes for a moment and imagine a place where, within the span of a single footstep, the temperature changes by more than 200 degrees Celsius. This place exists. You've already seen it. The moon. To understand the moon's temperature extremes, you have to understand what temperature actually is, what it means for a surface to be hot or cold. Temperature is a measure of the average kinetic energy of particles. Heat is transferred by three mechanisms: conduction, particles touching; convection, particles moving in bulk like air currents; and radiation, electromagnetic waves carrying energy through space, requiring no medium at all. Earth maintains a relatively stable surface temperature through all three mechanisms, but particularly through convection and the greenhouse effect of its atmosphere. The atmosphere absorbs solar energy, redistributes it across the globe through winds and ocean currents, and creates a thermal blanket that prevents the surface from radiating its heat away too rapidly at night. The result? Surface temperatures on most of Earth stay within a range that biological life can tolerate. The moon has no atmosphere, none. In direct sunlight, the lunar surface heats to approximately 127 degrees Celsius, above the boiling point of water at Earth's sea level. This is because the regolith absorbs solar radiation efficiently, and with no atmosphere to distribute that energy, it heats up dramatically. Rock and dust are also not great conductors of heat. The heat stays near the surface, concentrated in the top centimeter or so. In the lunar night, which lasts about 14 Earth days since the moon's day equals its orbital period, the surface temperature plunges to approximately minus 173 degrees Celsius. With no atmosphere to retain heat, the surface radiates its thermal energy away into space with startling efficiency. The temperature drop happens in hours as the sun sets. In the permanent shadow of polar craters, where the sun has not reached in billions of years, temperatures may reach minus 230 degrees Celsius, or even lower, making some regions of the moon among the coldest places in the inner solar system. The swing from maximum to minimum, approximately 300 degrees Celsius. But here is the detail that truly staggers. The transition is not gradual. Because the moon has no atmosphere to diffuse sunlight or distribute heat, the line between sunlight and shadow, the terminator, is a razor-sharp boundary. On one side of that line, the surface is around 127 degrees. On the other side, in shadow, it is already dramatically colder. A rock in direct sunlight and a rock a meter away in shadow can differ in temperature by hundreds of degrees. There is nowhere on Earth where such a thermal gradient exists so starkly in open air. Because on Earth, air distributes heat. The shadowed side of a sunlit rock may be cooler, but not hundreds of degrees cooler. This brutal thermal cycling has profound engineering implications. Materials expand when heated and contract when cooled. A metal component that cycles through a 300-degree temperature range twice every lunar day, once during the 14-day lunar daytime, once during the 14-day lunar night, is being subjected to enormous mechanical stress. Joints loosen, seals can fail, bolts work their way loose. The material fatigue that thermal cycling causes is a fundamental challenge for any equipment intended to operate on the lunar surface for extended periods. The Apollo equipment was designed for short stays, a few days at most. Even so, the astronauts noticed that the extreme temperatures affected their tools, their suits, and their equipment in ways that required careful management. Future habitats designed for long-term human occupation will need to deal with these cycles cleverly. Deeply insulating the habitat, perhaps burying it under meters of regolith, which itself acts as excellent thermal insulation, is one strategy. Building in the permanently shadowed craters of the polar regions, where temperatures are stable, if brutally cold, rather than wildly cycling, is another. And yet, there is something beautiful in the moon's extremes. The sharpness of the Terminator, the way shadows have edges like cut paper. The moon, unfiltered by atmosphere, shows the universe as it actually is, direct, unmediated, honest. Light hits and heat comes. Dark falls and cold follows. No fog, no haze, no warmth lingering in air that no longer exists. Just physics, doing what physics does. For most of the 20th century, scientists assumed the moon was dry. Bone dry. Barren of any chemistry involving water. The moon formed in heat and violence, had no atmosphere to trap volatiles, and was constantly being blasted by solar wind and micrometeorites. Whatever water might have existed on the young moon, the thinking went, had long since been stripped away and lost to space. And then the evidence started to come in, slowly at first, then in a flood. In 2009, NASA deliberately crashed a rocket stage into a permanently shadowed crater near the lunar South Pole, creating an impact plume that was then analyzed by the L-Cross spacecraft flying through it. The analysis revealed water vapor, real water, molecular H2O in the debris. The confirmation was startling and transformative. The moon has water. Not lakes, not rivers, not oceans, but water ice, deposited over billions of years in the permanent shadows of polar craters and preserved there by the extraordinary cold. These permanently shadowed regions, called cold traps, are some of the coldest places in the inner solar system, as cold as -230 degrees Celsius. And at these temperatures, water ice is essentially stable for geological timescales. It doesn't sublimate. It doesn't escape. It just stays. Where did the water come from? The answer is almost certainly from multiple sources. Comets and water-bearing asteroids have struck the moon throughout its history. When these impactors hit, some of the water they carried was vaporized by the impact's heat and lost to space. But some fraction of the water molecules, particularly those ejected at lower velocities and in directions that sent them toward the poles, eventually settled on the surface and migrated over thousands of years of thermal hopping across the sunlit surface into the cold traps. The solar wind is another source. Hydrogen ions from the sun continuously bombard the lunar surface, where they can interact chemically with oxygen-bearing minerals to form hydroxyl groups, OH, and potentially water molecules. This space weathering process may be a small but continuous source of water delivery. Additionally, volcanic outgassing from the moon's ancient geological past may have contributed water, as volcanic gases commonly include water vapor. NASA's Lunar Reconnaissance Orbiter, the Indian Chandrayaan-1 mission, and multiple other spacecraft have gathered evidence of water in various forms across the moon. Not just at the poles, but as hydroxyl. Groups spread more widely across the surface, detectable in infrared spectroscopy. In 2020, NASA announced findings from the Sophia Airborne Observatory confirming the presence of water molecules in the sunlit regions of the lunar surface. In Clavius Crater, one of the largest visible in Earth's sky. This was unexpected. If water could exist in sunlit areas, the chemistry of lunar water is more complex and more widespread than simple cold trap preservation would suggest. The significance of lunar water is enormous for human exploration. Water is heavy. Lifting water from Earth's surface into space requires enormous energy, currently costing roughly tens of thousands of dollars per kilogram to reach the moon. If water can be harvested from lunar ice deposits, it eliminates the need to carry it from Earth. But water is also, through electrolysis, a source of hydrogen and oxygen, the two components of rocket propellant. A moon with accessible water ice is a moon that could serve as a propellant depot, refueling spacecraft heading to Mars or beyond. This transforms the economic and logistical calculus of deep space exploration entirely. The moon's water has the potential to make it not a destination, but a way station, a harbor, a place to stop and resupply before heading further out into the solar system. It is one of the most exciting discoveries in lunar science of the past quarter century. And we barely knew it was there. It is one of the most ancient and intimate relationships in Earth's story. The moon's gravity, reaching across 384,000 kilometers of space, gently lifting the ocean. And in that lifting, that rhythmic, twice-daily variation of sea level that we call the tides, shaping the conditions in which life evolved. The tidal zone, the intertidal zone, is one of the most biologically rich and productive environments on Earth. It is the border between sea and land, a region that alternately exposed and submerged twice each day by the moon's gravitational influence. Organisms living here face extraordinary challenges: desiccation during low tide, submersion during high tide, changes in temperature, salinity, and oxygen availability. They must survive both marine and terrestrial conditions, and they do, in extraordinary abundance. Biologists have long speculated that the tidal zone may have been a critical environment in the evolution of animal life, particularly in the transition from aquatic to terrestrial life. Organisms forced to cope with regular exposure to air, regular cycles of wet and dry, may have been subject to selection pressures that favored adaptations, allowing survival out of water. Physiological innovations like enhanced desiccation resistance, air breathing, and the ability to move on land may have emerged precisely because tidal forcing repeatedly exposed marine organisms to terrestrial conditions. Some researchers go further, proposing that the rhythmic environmental cycles created by the tides, the regular alternation of stress and relief, may have driven evolutionary innovation more broadly, selecting for organisms capable of behavioral and physiological flexibility. The moon's influence on living things does not stop at the intertidal zone. Many marine organisms synchronize their reproductive cycles to the lunar month. Coral reefs, in one of nature's most spectacular mass-coordinated events, release vast clouds of eggs and sperm simultaneously. A spawning event triggered by lunar phase and water temperature that turns the ocean briefly milky with reproductive effort. The synchronization ensures that gametes from different coral colonies meet in the water column, maximizing the chance of fertilization. The trigger is the moon. The grunion, a small fish of the California coast, beaches itself in mass spawning events timed with exceptional precision to the highest tides of spring and summer. The females lay eggs in the wet sand, the males fertilize them, and then the tide retreats, leaving the eggs buried just above the high tide line, safe from predation, incubating in the warm sand for 2 weeks until the next high tide comes to wash the juveniles into the sea. The entire reproductive strategy depends on the moon's gravitational calendar. Horseshoe crabs, ancient animals with a lineage stretching back 450 million years, gather in vast numbers on Delaware Bay beaches each spring to spawn, timed to the highest tides of May and June. The synchronization is so precise and the numbers so vast that the event has shaped the ecology of the entire mid-Atlantic coast. Even in terrestrial environments, lunar rhythms are deeply embedded in the biology of many organisms. Various insects, including certain species of midges and mayflies, emerge and swarm in synchrony with the lunar cycle. Some terrestrial mammals show behavioral cycles loosely tied to lunar phase. The question of whether the moon affects human biology and how is more contentious. Folk traditions from virtually every culture on Earth have claimed that the moon affects human sleep, behavior, fertility, mental health, and bodily processes. The word lunatic comes from the Latin for moon, reflecting the ancient belief that the full moon influenced mental states. Lunacy was once a genuine medical term. Modern scientific studies of lunar effects on human physiology and behavior have produced a mixed picture. Some carefully controlled studies have found small but measurable correlations between lunar phase and human sleep patterns. Specifically, that sleep duration and depth may be slightly reduced around the full moon, even in controlled environments without windows. The proposed mechanism involves subtle changes in Earth's magnetic field around the full moon, or, more controversially, direct moonlight effects on melatonin production. Other studies find no such correlation when confounding variables are carefully controlled. The scientific consensus, to the extent one exists, is that the moon's direct gravitational and electromagnetic effects on individual human physiology are extremely small. The tidal differential across a human body is roughly 100 billion times smaller than the tidal force on the ocean. But the research is ongoing, and the moon's connection to biological rhythms in the broader sense, to life itself, is real and ancient and profound. The tide comes in, the tide goes out, and somewhere in that rhythm, life learned to live. Long before Newton could explain gravity, long before telescopes could show the moon's craters, long before any human being knew what the moon was made of, humans were watching it, naming it, building meaning around it. Every culture in every corner of the world developed mythology around the moon. The Norse saw Mani, the moon god, driving his chariot across the sky. The ancient Greeks saw Selene, a silver goddess pulling the moon behind her own chariot. In Japan, the moon is associated with the rabbit, a creature some people can still trace in the pattern of the lunar Maria, the dark regions that look, with imagination, like a rabbit pounding something in a mortar. In Mesoamerica, lunar deities were central to the great cyclical calendars that governed civilization. In China, the moon festival celebrates Chang'e, a woman who flew to the moon and lives there still, with a white rabbit as her companion. There is something worth sitting with here. These myths, despite their enormous diversity of detail and character, share a common feature. They all treat the moon as alive, as personal, as meaningful, as something more than a rock in space. The moon in human mythology is never just a physical object. It is a presence, a being, something that watches and is watched. Science has replaced the mythology, but it has not, perhaps, replaced the feeling. Because when you spend time actually learning about the moon, really learning about it in the depth and strangeness that modern science provides, you encounter something that feels, emotionally, a little like what the myths were reaching for. Not a god, not a goddess, not a guardian spirit, but something vast and ancient and consequential. Something that has shaped this world and us in ways we are still discovering. Something that, despite being only a rock, turns out to matter profoundly. The moon affects our tides. It stabilizes our axis. It has shaped the evolution of life. It was born from the same materials as our own world. It is leaving slowly and has been since long before our species existed. Science does not diminish the moon. It makes it stranger, more real, more worthy of awe. And perhaps this is what the ancient myth makers were doing, in their own way, trying to hold the moon's strangeness, trying to give it a face and a story so that its mystery could be inhabited rather than just observed. They didn't have the equations. They didn't have the seismographs or the spectroscopy or the lunar samples. But they had eyes and minds and the deep human need to understand what lies above. The instruments have changed. The need has not. There is something hidden beneath the moon's surface that most people have never heard of. Not just rock, not just magma. Though there was magma once, billions of years ago, flowing beneath the surface in channels called lava tubes. Channels so large and so structurally robust that when the lava eventually drained away, leaving empty tunnels behind, some of them didn't collapse. Some of them are still there. Lava tubes are familiar on Earth. They form when flowing lava creates a hardened crust over itself while still flowing beneath, essentially insulating and channeling the lava stream. When the eruption ends and the lava drains away, a hollow tunnel remains, sometimes quite large. Lava tubes in Hawaii and on the Canary Islands can be tens of meters wide and kilometers long. On the moon, the same process occurred, but the moon's lower gravity, only about 1/6 of Earth's, means that lava flows could form tubes dramatically larger than anything on Earth. Calculations suggest that lunar lava tubes could be tens of kilometers wide and hundreds of kilometers long, with roofs perhaps 1 to 2 kilometers thick. If even some of these tubes are intact, if the roof has not collapsed over the past few billion years of micrometeorite bombardment and moonquakes, they represent one of the most extraordinary potential environments in the solar system. Why? Because the interior of a lunar lava tube would be extraordinarily sheltered compared to the surface. The surface of the moon is hostile in multiple ways. Extreme temperature swings, intense solar radiation, cosmic ray bombardment, and the constant light rain of micrometeorites. A lava tube interior is shielded from all of these. The thick rock roof blocks radiation, the enormous thermal mass of the surrounding. Rock stabilizes the temperature. Computer models suggest that lava tube interiors might maintain a temperature around -20 to -30 degrees Celsius, cold but remarkably constant compared to the 300-degree swing on the surface. The micrometeorite risk is essentially eliminated. A lunar lava tube, if accessible, would be one of the most naturally hospitable environments on the moon. A ready-made shelter, radiation protected, thermally stable, available without any need for construction. For mission planners thinking about long-term human habitation on the moon, lava tubes are deeply compelling. Building adequate radiation shielding for surface habitats requires thick walls of regolith or water, both of which add mass and complexity. A lava tube provides all the shielding naturally. You simply build your habitat inside it. The confirmed existence of specific, accessible lava tubes on the moon is still being established. The pit entrances, skylights where a section of the tube roof has collapsed, have been identified by NASA's Lunar Reconnaissance Orbiter in the Marius Hills region of the near side and at other locations. These pits are visible as dark holes, dozens to hundreds of meters across, with sloped walls where the collapsed material has slid downward. Whether these pits are entry points to extensive intact tube systems or simply isolated voids is not yet known. A future robotic mission, potentially lowering a small rover on a cable through the pit entrance to explore below, could answer this question definitively. The caves of the moon may be waiting, enormous, dark, silent, and ancient. We are not done with the moon. We went there, pulled back, waited, and now we are returning. The reasons are scientific, economic, geopolitical, and something harder to name. A kind of pull, a sense that the moon is not just a destination, but a threshold. The first step in something much larger. NASA's Artemis program, named for the Greek goddess of the moon and twin sister of Apollo, is the initiative designed to return humans to the lunar surface. The program aims to land the first woman and first person of color on the moon, establishing a sustained human presence there rather than the brief visits of the Apollo era. Artemis is not just an American program. It involves space agencies and private partners from across the globe under the framework of the Artemis Accords, a set of agreements governing the norms of behavior for lunar activities. The Gateway, a small space station planned for lunar orbit, would serve as a staging point for surface missions, allowing astronauts to transit between Earth and the surface in stages, and enabling missions to multiple locations rather than requiring each crew to travel the full Earth-Moon distance from scratch each time. On the surface, the vision is ambitious. Not just brief visits, but extended stays. Habitats, scientific stations, mining operations. The moon's resources have become a subject of serious economic and geopolitical interest. Beyond water ice, the lunar regolith contains substantial quantities of useful materials: iron and titanium for construction, silicon for solar cells, aluminum, and a variety of rare materials. The Highlands and Maria have different compositions, offering different resource profiles. Perhaps the most discussed resource, though, the one that has attracted the most speculative attention, is helium-3. Helium-3 is a rare isotope of helium, an atom with 2 protons but only 1 neutron, unlike the common helium-4 with 2 of each. On Earth, helium-3 is extraordinarily scarce. Only about a few hundred kilograms exist on the entire planet, mostly as a byproduct of nuclear weapons maintenance. But helium-3 has been implanted into the lunar regolith by billions of years of solar wind bombardment. Estimates suggest the moon may contain 1 million metric tons of helium-3. Why does this matter? Because helium-3 is a theoretically excellent fuel for nuclear fusion, the process of combining light atomic nuclei to release energy, the same process that powers the sun. A deuterium-helium-3 fusion reaction would be far cleaner than conventional deuterium-tritium fusion, producing fewer neutrons and therefore generating much less radioactive waste. If commercial fusion power ever becomes reality, a goal that has been 30 years away for the past 70 years, though recent progress at facilities like the National Ignition Laboratory has been genuinely encouraging. Helium-3 from the moon could be an extraordinarily valuable fuel source. The energy content of a single ton of helium-3 used in a fusion reactor is estimated to be equivalent to roughly 14 million tons of coal. The economics are staggering if the technology ever arrives. Countries and companies with this future in mind are increasingly interested in establishing a presence on the moon. China's Chang'e program, which has successfully landed multiple missions including the historic Farside landing, has expressed explicit interest in the moon's resources. The United States, the European Space Agency, Japan, India, and private companies are all moving toward the moon with varying timelines and ambitions. But there is a view from the moon that transcends the economics and the geopolitics and even the science. It is the view of Earth. From the surface of the moon, Earth is not a distant point of light, but a disk, a full, round, blue and white and tan sphere, hanging in a black sky, turning slowly, showing its face to you as your own sky used to do to it. You can see the oceans, sometimes the cloud systems. At night, the lit side of the spinning Earth glows with the accumulated light of billions of human lives. Every person who ever went to the moon came back changed by that view. They describe it in similar terms. These 12 explorers, small, alone, fragile, beautiful. A sense that the divisions that seem so significant from the surface, the borders, the conflicts, the distances between people, are invisible from there. That the only meaningful category from the moon is human. Edgar Mitchell, who walked on the moon during Apollo 14, described having an experience returning to Earth in his spacecraft, of suddenly perceiving the universe as, in his words, somehow in some way conscious. A flash of awareness, looking at the Earth and moon and stars, that the universe was not a collection of dead objects, but something alive and interconnected. He spent the rest of his life trying to understand and communicate what he felt in that moment. Science has not validated Mitchell's intuition, but it has not dismissed the feeling behind it, because there is something in the moon's story. In its improbable birth, its perfect alignment with the sun, its stabilizing influence on our world, its ancient craters and frozen dust, and patient recession, that resonates beyond data. Something that touches, if you let it, the part of you that lies under the words and the facts and the careful reasoning. Something that has no name. Science is often described as a process of answering questions. And it is. But the best science, the deepest science, the science at its most alive, is equally a process of discovering new questions. Of finding that every answered mystery opens a corridor to 3 new ones. The moon is full of these corridors. We know that it formed from a giant impact, but we don't know exactly how. We know that it has water ice at its poles, but we don't know its full distribution or how it got there. We know that the near side and far side are dramatically different, but we don't know why the crust is asymmetric. We know the moon is geologically dead, but the definition of dead in geology is fluid, and some scientists are not sure the moon is entirely finished. In 2022, researchers analyzing data from the Lunar Prospector mission revisited evidence for a very small, partially molten zone deep in the moon's interior. A region that might still contain some liquid or partially molten rock. This is not a large amount of internal heat, but it complicates the picture of a completely cold and inactive moon. The question of whether the moon could still experience volcanic activity, even on a small and infrequent scale, has not been definitively settled. The permanently shadowed craters at the poles remain almost entirely unexplored at surface level. We know they contain ice, but we don't know the full chemistry of the polar deposits, whether they contain other volatile compounds like ammonia, methane, or even organic molecules that might have been delivered by cometary impacts over billions of years. The poles of the moon might be, in a sense, a chemical library of the solar system's history, a frozen record of what the inner solar system has been delivering to terrestrial surfaces over geological time. The moon's magnetic field, or rather its apparent lack of a global magnetic field, combined with strongly magnetized regions of crust called magnetic anomalies, is another deep puzzle. The moon has no global magnetic field today, but many areas of its surface are strongly magnetized, suggesting that it had a significant magnetic field in its distant past. How it generated and then lost that field, and why the field left such irregular imprints on the crust, is not fully understood. The Rhina Gamma region on the near side, a striking bright swirl on the lunar surface visible in amateur telescopes, is one of the largest and most dramatic magnetic anomalies. The swirls appear to be regions where the solar wind has been deflected by the local magnetic field, and where the resulting pattern of ion deposition has preserved the surface brightness in a way that creates the beautiful, comma-like shapes. But the origin of the magnetism itself, why that region is so strongly magnetized, is not well understood. Some researchers have proposed that the Rhina Gamma and similar swirls might be associated with the ancient impact of a large comet. When a comet strikes a magnetized planet or moon, the comet's own magnetic field, carried in its ionized coma, could imprint itself onto the surface. This magnetic comet impact hypothesis is intriguing but unverified. Then there are the questions we haven't thought to ask yet. Every time we return to the moon, every new mission, every new instrument, every new analysis of existing data, we find something unexpected. The data never run out of surprises. The Lunar Reconnaissance Orbiter, orbiting the Moon since 2009, has produced extraordinary data. High-resolution maps of the entire surface, temperature maps, UV reflectance maps, radar maps showing subsurface structure to depths of several meters. And within that data, researchers keep finding things that weren't expected. Recent topographic analyses have found networks of features that look like the dried channels of ancient water flow, not on the surface, but in the subsurface, possibly the remains of ancient drainage systems from a period when the moon might have briefly had a tenuous atmosphere and warmer conditions. This is highly speculative and not yet confirmed, but it illustrates how, even now, the moon can present us with something genuinely new. We have visited, we have sampled, we have photographed and mapped and listened. We have bounced lasers off its mirrors and measured its gravity field and mapped its chemistry from orbit. And still it is not fully known. It will not be fully known in our lifetimes. Perhaps that is appropriate. Eugene Cernan was the last human being to walk on the moon. He knew it as he did it. He had time to feel it. Before climbing the ladder of the Lunar Module Challenger for the final time, Cernan knelt down in the dust of the moon and traced the initials of his daughter, Teresa Dawn Cernan, in the grey regolith. TDC. Those letters are still there. They will be there for millions of years. His last words, spoken as he climbed the ladder, were, "We leave as we came, and God willing as we shall return, with peace and hope for all mankind." That was December 14th, 1972. We have not returned. More than 50 years have passed since any human being stood on another world. An entire generation has been born and grown old, and many have died. Without any of this species, they belong to stepping outside the thin membrane of its own planet. We have sent robots, extraordinary robots, cameras and wheels and spectrometers, tirelessly exploring and transmitting, but not ourselves. The moon has waited. The Artemis program envisions a return in this decade. Whether it happens on schedule or not, whether it is next year or the decade after, there is a particular feeling in knowing that it is coming, that human footprints will again be pressed into that ancient dust, that someone will look up from the moon's surface and see the whole Earth hanging in the black sky and feel what every astronaut who ever did it described: the silence, the beauty, the smallness, the irreplaceable preciousness of that blue-green disk. Perhaps they will feel what Cernan felt. Perhaps they will feel something new. That's the nature of being the first to go somewhere unprecedented. You don't know what you'll feel until you're there. Let us pause for a moment at the edge of what we know. We have traveled through the moon's history, from its violent birth in the aftermath of an ancient planetary collision, through its slow orbital retreat, through its locked and hidden face, its ringing interior, its brutal temperatures, its dangerous dust, its precious ice, its influence on every tide and every tidal zone where life has ever evolved. We have stood at the edge of its mysteries, the asymmetry of its hemispheres, the magnetism of its swirled crust, the possible lava tubes still yawning beneath, its surface, the chemistry of its polar shadows, and we have stood quietly before the fact of those boot prints. 12 people. 12 names, 12 pairs of boots pressing into lunar dust, all still there in that grey and airless stillness, waiting. What does it mean to know all of this? I think it means something different for everyone who encounters it. For some, the moon's physics and chemistry and geology are fascinating on their own terms. Puzzles to be solved, mechanisms to be understood, data to be gathered and analysed and published. That kind of knowing is its own reward, complete and rigorous. For others, the moon's story opens into something larger, into questions about what it means to be a small, conscious species on a small planet orbiting a small star in an ordinary galaxy, looking up at the rock that shares our orbit, that shapes our tides and stabilizes our axis, that was born from the same catastrophe that made our world. Questions about contingency and meaning and improbability. If Theia had struck at a slightly different angle or a slightly different speed, the moon might not have formed. Without the moon, Earth's axis might have wobbled wildly over geological time, and complex life might never have emerged. No complex life would mean no nervous systems, no curiosity, no telescopes, no science. We exist because of a collision that happened 4.5 billion years ago. We are, in a sense, the children of the moon, and the moon is leaving us. Slowly, at the rate your fingernails grow, year after year, century after century. By the time the sun expands and the solar system ends, the moon will be farther away than it has ever been. And the total solar eclipses it creates, those brief and perfect alignments of cosmic coincidence, will already be long over, replaced by the ring of light around a disk that no longer quite covers the sun. The window of total eclipses is a gift of timing. We happen to be alive in it. All of this is passing. Everything in the universe is passing. The moon's position, the sun's brightness, the shape of the continents, the species that live on them. Change is the universe's deepest nature, but the moon is patient with change. It has been here for 4.5 billion years. It has watched the Earth cool and erupt and flood and freeze and bloom with life. It has watched species rise and vanish and be replaced by new ones. It watched, from its fixed remove, as one particular species of ape developed a big brain and started asking questions about where the moon came from. And the moon is still here, answering. Not with words, never with words, with light, with tides, with the slow, reliable rhythm of its phases, new to full, to new again, counting off the weeks, counting off the months, counting off the years. Step outside tonight if the sky is clear. Look up. You'll find it easily. You always have, your whole life. That familiar circle of silver light, that ancient face that humans have been staring at since before language, since before fire, since before the first word was ever spoken aloud. And remember what you know now. Remember that it was born in violence, in a collision so enormous that it remade two worlds. Remember that it has been slowly leaving, drifting millimeter by year, away from the planet it circled in its blazing youth. Remember that it holds one face toward you always, that its far side has never once looked at human eyes from the ground, that beneath its surface the ghost of ancient lava rivers may still lie open in the dark. Remember the dust, fine as smoke and sharp as glass. Remember the boot prints perfectly preserved, the initials of a child traced in lunar regolith by a father about to leave for the last time. Remember the ice, hiding in the ancient cold of polar shadows, patient and frozen and full of possibility. Remember that without it, the tides that shaped life on this planet might never have formed the way they did, that the axis you're standing on, the axis that gives you seasons and weather and the rhythms of the year, is steadied in part by its gravity. That the eclipse you might someday be lucky enough to see, that impossible, transcendent moment of totality, is only possible because of a cosmic coincidence so precise that it works only now, only in this narrow window of Earth's history, only on this particular planet. We have told you many facts tonight. We have given you mechanisms, numbers, hypotheses, histories, and all of them are true to the best of science's current understanding. But there is one thing that all the facts laid end to end cannot quite capture. And that is the simple physical experience of standing on the Earth and looking at the moon and feeling, not thinking, just feeling, the scale of it, the age of it, the silence of it. The moon has no sound, no wind passes across its surface, no bird calls from its highlands, no river rushes through its craters. It has been silent since before the oceans of Earth formed. It will be silent long after our oceans are gone, but it makes a sound in us, something below language, below thought. A resonance that we have been feeling for as long as we have been capable of feeling anything at all. The oldest light we know, the closest wilderness, the most familiar mystery. Thank you for spending this time with us, with the moon, with science, with wonder. If this documentary has given you something to carry with you, a question, a small shift in how you look at the sky, a new way of understanding that familiar silver face, then it has done what we hoped. We are infinite science, and there is so much more waiting in the dark between the stars to be discovered. If this journey has resonated with you, please consider subscribing to the Infinite Science channel and leaving a comment below with the part of the moon's story that struck you most. Your support allows us to keep exploring these extraordinary mysteries, the moon, the planets, the galaxies beyond, the deep questions that lie at the edge of what we know. Ring the notification bell so you don't miss the next journey, because we have barely scratched the surface, and the universe is patient. It will wait for us to keep asking. In the 1960s, as NASA was preparing to land humans on the moon, mission controllers noticed something strange. The trajectories of lunar orbiting spacecraft were not quite right, not dramatically wrong, not enough to cause the missions to fail or the spacecraft to be lost, but measurably, consistently wrong. As spacecraft passed over certain regions of the lunar surface, particularly over the large dark Maria on the near side, their orbits would shift slightly. They would speed up a little, then slow down again. The effect was small, but it was real, and it was repeatable. It happened at the same locations every orbit. The cause was something no one had quite anticipated. Concentrations of dense mass beneath the lunar surface, creating regions of slightly elevated gravity that pulled passing spacecraft toward them. These features came to be called mascons, short for mass concentrations. The mascons correspond almost exactly with the moon's large impact basins, the same basins that were later flooded with lava to create the Maria. The connection is not coincidental, but the precise mechanism by which an impact basin produces a mass concentration beneath it has been a matter of scientific debate. One explanation involves the impact itself. When a very large asteroid strikes the moon and excavates a basin, it removes a huge volume of material from the surface. The mantle, no longer pressed down by the weight of that material, rebounds upward, a process called isostatic rebound. The mantle material that rises is denser than the crust material that was removed, and this plug of dense mantle rock beneath the basin center creates elevated local gravity. The subsequent flooding of the basin by lava adds another layer of dense material. Basaltic lava is denser than the highland crust, contributing further to the gravity anomaly. NASA's Grail mission which flew twin spacecraft in close lunar orbit from 2012, produced the most detailed map of the Moon's gravity field ever made. The twin spacecraft, named Ebb and Flow by schoolchildren in a contest, flew in formation, measuring the distance between themselves with extraordinary precision. As the lead spacecraft passed over a dense region, it would accelerate slightly, pulling away from the trailing spacecraft before the trailing one arrived over the same region and accelerated in turn. The changing distance between the two spacecraft encoded the Moon's gravitational field with extraordinary resolution. The Grail data revealed not just the major mascons, but a much more complex picture of the Moon's interior, ancient tectonic features, the density structure of the crust, the ghostly remnants of very old impact basins that have been largely erased from the surface, but whose gravitational signature remains. The Moon's crustal thickness varies from almost zero at some impact basin centers to over 60 kilometers in the highlands. The average density of the crust differs between the near and far sides. The gravity map is, in a very real sense, a portrait of the Moon's interior. A portrait painted not in light, but in the tiny tugs and pulls of hidden mass. The mascons have a practical significance for any long-term human presence on the Moon. Spacecraft in low lunar orbit are continuously affected by them. Their trajectories must be regularly corrected, using propellant, to prevent the mascons from gradually pulling them into unstable orbits or driving them into the surface. Future orbital stations around the Moon will need to account carefully for the Moon's irregular gravity field, choosing their orbits wisely to minimize the propellant cost of maintenance. But there is also something philosophically interesting about the mascons. They are a memory. Encoded in the Moon's gravity field, encoded in the very way the Moon pulls on passing objects, is a record of impacts that happened billions of years ago. The mass distributions created by those ancient catastrophes are still there, still affecting every spacecraft that flies overhead, still telling the story of the Moon's violent past in the only language that gravity knows. Matter remembers. Even when the surface has been reshaped, even when the evidence has been partially buried and eroded, the density anomaly persists. The gravitational fingerprint of an ancient asteroid strike, billions of years gone, is still pulling on the world around it. The Moon keeps its history in its weight. The Moon did not merely shape the Earth, it shaped human civilization. Before clocks, before written calendars, before astronomy, before mathematics, people could tell time by the Moon. The monthly cycle from new to full and back again is one of the most reliable, visible, and universally accessible patterns in nature. In a world without written records, a world where time had to be tracked by direct observation of the sky, the Moon was the most useful clock available. The word month comes directly from the Moon. In English, the etymology is transparent: month from moon. In Latin, mensis, both for month and for moon. In Greek, mene for moon, from which we derive menstrual, reflecting the ancient observation that the human reproductive cycle approximates the lunar cycle. In Arabic, Qamar for moon, and the Arabic calendar, the Islamic Hijri calendar, is a purely lunar calendar in which months follow the visible lunar cycle precisely. Nearly every civilization in human history has organized its time by the Moon's phases. The Mesopotamian civilizations, Sumer, Babylon, Assyria, used lunar calendars and developed sophisticated methods for predicting the Moon's behavior, including the Saros cycle, a period of approximately 18 years, 11 days, and 8 hours after which lunar and solar eclipses repeat with remarkable regularity. Babylonian astronomers tracked this cycle with tables of astonishing precision, centuries before Greek astronomy systematized celestial observation. The ancient Egyptians used a combined solar-lunar calendar. The Maya developed an extraordinarily precise calendar system that tracked the moon's cycles alongside the solar year and the Venusian cycle, and could predict eclipses centuries in advance. The Chinese lunisolar calendar, still used to determine the dates of the Lunar New Year and other traditional festivals, has been refined over thousands of years and remains in use today. The 29.5-day synodic month, the time from new moon to new moon, is not commensurate with the 365.25-day solar year. 12 lunar months give you about 354 days. 13 give you about 384. Neither matches the solar year exactly. This incommensurability has been the central challenge of calendar making across all human civilizations: how to reconcile the moon's rhythm with the sun's. Different cultures solved this differently. Some abandoned the moon entirely, adopting purely solar calendars. The Roman Julian calendar and its successor, the Gregorian calendar, which we use today in most of the world. Some kept purely lunar calendars, accepting that the calendar months drift through the seasons. The Islamic calendar, in which Ramadan falls in different seasons in different years, rotating through the solar year over a 33-year cycle. Some developed lunisolar calendars, intercalating a leap month at regular intervals to keep the calendar roughly aligned with both the moon and the sun. The Hebrew calendar, the Chinese calendar, the Hindu calendar. The moon forced us to think about time. It gave us our first units. It drove the development of mathematics, astronomy, and systematic observation. The tables of eclipse predictions made by Babylonian astronomers required careful record-keeping over generations, and the effort of maintaining those records built institutions of knowledge that eventually, very slowly, became science. We still celebrate by the moon. Easter is determined by it, the first Sunday after the first full moon after the spring equinox. Ramadan begins when the crescent moon is sighted in the western sky after sunset. The Lunar New Year, Diwali, Rosh Hashanah, Vesak. The great festivals of major world religions and traditions are anchored in the moon's phases. The moon is not just science, it is culture, woven so deeply into human life that we carry it without thinking. We live inside its rhythm still. The moon has an atmosphere, barely. Technically, what surrounds the moon is classified as an exosphere, a region so tenuous that the particles within it rarely collide with each other, each atom or molecule essentially following its own ballistic trajectory without interacting with its neighbors. It is an atmosphere in the same sense that a single snowflake is a blizzard. The total mass of the moon's exosphere is estimated at approximately 10,000 kilograms. About the weight of 2 African elephants distributed across the entire envelope of the moon. Compared to Earth's atmosphere, which masses roughly 5.15 times 10 to the 18th kilograms, the moon's exosphere is essentially nothing. And yet, it is not nothing. The exosphere contains several identified species, sodium and potassium, released from the lunar surface by solar radiation and meteoroid impacts. Helium, delivered by the solar wind. Argon, possibly outgassed from the lunar interior. Hydrogen and oxygen, created by the interaction of solar wind protons with surface minerals. And traces of other elements released by the perpetual micrometeorite bombardment that liberates atoms from the regolith. Sodium, in particular, creates a faint sodium tail extending away from the moon in the Idean anti-sunward direction, detectable by sensitive sodium line filters on Earth-based telescopes. The moon has a tail like a comet, invisible to the naked eye, but real. The exosphere is dynamic. It changes with the time of day, with the lunar cycle, with solar activity. On the day side, the sun drives electrons from dust particles and creates an electrostatic environment that can levitate fine dust into the near-surface exosphere. This levitating dust was possibly observed by instruments on the Surveyor landers in the 1960s and by Apollo astronauts who reported a mysterious glow on the lunar horizon near the terminator, possibly caused by dust levitated by electrostatic forces, scattering sunlight. The concept of a lunar atmosphere may seem trivially thin, a curiosity rather than a significant feature. But it matters in surprising ways. It matters because even an exospheric density atmosphere means the moon is not a perfect vacuum, and understanding its chemistry and dynamics gives us insight into how other airless bodies in the solar system, Mercury, large asteroids, the moons of other planets, exchange material with the solar wind and maintain their thin envelopes. It matters because the exosphere interacts with the surface. Atoms kicked off the surface by impacts or solar radiation eventually return to the surface or escape to space, and the chemistry of this cycle affects the top layers of the regolith. And it matters because future human activities on the moon, rocket launches, industrial operations, even human respiration leaking from habitats, will add to the exosphere. A busy human presence on the moon will change its atmospheric composition measurably. The moon's thin breath is not immutable. It is vulnerable to the presence of a species that exhales, burns fuel, and outgazes the materials of its technology. We will, in this small way, leave our chemical mark on the moon's sky. Perhaps there is something humbling in this, that even on an airless world, even in a space so thin that it barely qualifies as matter, we would arrive and immediately begin to change things. It is what we do. It is who we are. The question is whether we will do it wisely.